Hello and welcome everyone. We are live on this particular channel of Unacademy J English, and in this session we are going to talk about magnetism. Magnetism, basically we are going to cover the theory portion as well as PYQ, some PYQs, not all the PYQs, but we will take some illustrations so that we can understand the concept very deeply. We can revise all the things, we can revise all the theory, formulae, some examples, some PYQs, all those things we are going to cover in this particular session. So first of all, let me start from the one thing, very important thing, that we are launching our new batches. If you have seen the RM 2025, then you have must seen these Nimbus batch for class 11th, Nexus batch for class 12th, and this Phoenix batch for droppers. If you are any one of these, then you can take the batch any one of this. If you are class 11th, class 12th, then you can get the best anything you can. It is here. Okay, so let us start from the very beginning. Magnetism. What is magnetism? We'll talk about all the concepts, all the theory, but not in the detailed way. We'll just take a look on every concept, each and every concept in a short manner, and also we're going to take some examples, some figures, as I said earlier. Okay, let us start from the very beginning. I'll tell you that what was the magnetism introduced, how we can understand the magnetism. So if there is a wire and in that particular wire the current is flowing, some kind of, any kind of wire, it can be in any shape, it can be rectangle, it can be circle, it can be a simple straight wire, any kind of wire is if there is, then in this wire, if we just flow a simple current, not time varying current, simple current, then in that particular wire, around that particular wire, there is a magnetic field. Now the question is, if there is a magnetic field, how we can just say that there is a magnetic field? With the help of any needle. If you will just put a needle near a current carrying conductor, then it will show a deflection along the magnetic field. Nice. Okay, so first of all, let me tell you one thing, that if we have the magnetic field, now we have two things. What kind of two things? That the question is, if we have magnetic field, then we have to find two things. First of all, what is the value of magnetic field? What is the magnitude of the magnetic field? What is the direction of magnetic field? This is the first aspect. Okay, so magnetic field, we have two aspects. Magnetic field. So what are the two aspects? That if we have a magnetic field, then there will be some magnitude of it. So first of all, what is the value of magnetic field, right? So first aspect is how to find the value of magnetic field. Second aspect, that if we have magnetic field, in that particular magnetic field, if we just put a charge and we just throw it in somewhere, in any direction, it experiences a force. And if a charge is experiencing a force, then we must know that the direction as well as the magnitude of the force, so that we can calculate where the particle will go or what will be the basically path of the particle. So the second aspect is magnitude or the just force, magnetic force. So magnetic force. So in the magnetism, these are the only two aspects which we are going to talk about. First of all, what is the value of magnetic field? Secondly, what is the value of magnetic force? So if we talk about the value of magnetic field, there are two laws which give the value as well as the direction of the magnetic field. What are those two laws? Those two laws are, first of all, Barrett-Savart law, and second is Ampere's circuital law. So these two laws are basically give the expression of magnetic field, that what is the, and if I say about the Barrett-Savart law, this is the more expanded form of magnetic field. Like if I should say that if we have any kind of system, it can be symmetric, it can be unsymmetric. Like suppose we have a short wire. Okay, now we have just a short wire and we have just flown the current through it. Now we have to find the value of magnetic field near this particular wire. So we can calculate the value of magnetic field with this Barrett-Savart law, but we cannot find the value of magnetic field near this short wire because of this Ampere's circuital law, with this Ampere's circuital law, because it just gives the value of magnetic field in symmetric system, I should say, because the symmetric systems like an infinite wire, like a ring, these are the symmetric systems. So we can find the value of magnetic field within the symmetric systems with the help of Ampere's circuital law. And Barrett-Savart law is a universal law. This is also universal law, but we cannot apply the Ampere's circuital law. This we can apply anywhere, any kind of system, whether it is symmetric, whether it is non-symmetric, any kind of system. Got it? Okay. Now, first of all, these two laws I have said, that Biot-Savart law and Ampere-Circuitor law. These are the two laws which help to calculate the value of magnetic field. Next, what is the Biot-Savart law? First of all, I'll just write expression. Suppose that it is a simple wire in which current I is flowing, and this segment I have taken length dl and other distance r at an angle theta. We have to find the value of magnetic field. What is the value and direction of magnetic field? dB, that is equals to mu naught by 4 pi I dl cross r, I dl cross r divided by mod of r cube. This is the Biot-Savart law. This is the Biot-Savart law. If we talk about this is the vector form of Biot-Savart law, I should say. But if we are talking about the scalar form, we should just write dB, that is equals to mu naught I dl sine theta upon 4 pi either r square. This is the scalar form. This is the scalar form, not non-vector form of the Biot-Savart law. Basically, with this Biot-Savart law, we can find the value of magnetic field in the lot of cases. First of all, if we talk about the direction of magnetic field, we are first, because this is a vector, right? So direction can be also find in this particular thing. So what we have to do, we just have to put our fingers in the direction of dl. Suppose that this is the length dl, right? Or dl, we can take the direction of current also. Okay? So this is the direction of dl, and we have to curl it towards r. So if this is dl and this is r, so dl cross r means thumb is inside, so thumb is giving the direction of magnetic field on this particular point. So this is the method that how we can find the value as well as the direction of magnetic field at any point near a current carrying conductor. Okay, next thing. We have told you that what is the direction of magnetic field. Okay, next thing. Next thing is basically there are a lot of application. There are a lot of application of the Biot-Savart law. There are a lot of application of the Biot-Savart law. First of all, let me tell you one thing, that if we have just a wire, finite wire, if we have just a finite wire and we have to find the value of magnetic field near a finite wire. So this is the finite wire, current I is flowing, this is the radius r, this is the angle theta 1, this is angle theta 2, and here we have to find the value of magnetic field. So there is just one component around this particular wire. What is the component? It is inside. If we are saying that current is going upside, so value of magnetic field B is equals to mu naught I by 4 pi r sine theta 1 plus sine theta 2. This is the value of magnetic field at this particular point. Now there is another method which with which we can find the value of, or we can say the direction of magnetic field at this particular point. We just have to put our thumb in the direction of current and curl your fingers, and in the direction where we have to find the magnetic field, you will just curl the finger. So if this is the direction of current, we'll just put the thumb and we'll just curl the finger. It means this is going inside, means the magnetic field is inside. Any confusion? So this is the value of magnetic field near a finite wire. If we say there are two types, like semi-infinite and finite. So if we talk about the semi-infinite, so for semi-infinite, theta 1 is equals to 0, or we can say this point can be here, right? And theta 2 is equals to 90. Okay, it means one side is infinity, one side is finite. Okay, so here the magnetic field will be B is equals to mu naught I by 4 pi r. If you just put the values of theta 1 and theta 2 here, you'll just get this expression. Okay, next we talk about the infinite wire. Infinite wire. If we talk about the infinite wire, we should say that theta 1 is equals to theta 2 is equals to 90 degree. It means B is equals to what? Mu naught I divided by 2 pi r. Got it? Any confusion till here? Now, if we talk about the ring, any kind of ring in which current I is flowing, the radius r, then in the case of ring, this is the ring, current I is flowing, radius is r, at the center B is equals to mu naught I divided by 2r. This is the value of magnetic field. Or if we have the half ring, suppose we have the half ring or semicircular ring, So in the case of half ring or semicircular ring, we just have a structure like this. So this is radius r, this is supposed current I, and if there is any kind of loop, just listen to me very carefully. If there is any kind of loop, it can be a circle, it can be a semicircle, it can be any kind of shape, a random shape. So if there is any loop, then you'll have to find the value of magnetic field at the center. Then what you have to do, you just have to curl the finger in the direction of current. The thumb will give the direction of magnetic field. So this is the current. So just curl your finger in the direction of current. Value of thumb is giving the direction of magnetic field, or that the direction of thumb is giving the direction of magnetic field. Okay. So at this particular point, V is equals to what? Mu naught I divided by, this is half, right? So 4R. This is mu naught I by 4R. So if we have quarter ring, so in the case of quarter ring, what? Just imagine it will be 8R. So B is equals to half of this, means mu naught I by 8R. Mu naught I by 8R. So this is the value of magnetic field as a center of a quarter ring, right? Okay. Next, if we have a like arc, if we have an arc length, so simply we just have to put the value of there here. Theta should be in radians. It should be in radians. I'm not going to just explain the proof. You just have to see that it is the value of magnetic field, and it is because of this arc. Very good, very good. Okay. Next thing, there are a lot of problems, like if we have some kind of system like this, suppose that our system like this, now these kind of problems are being asked in the JEE Main examination on the very frequent basis, right? Okay, great. So first of all, suppose the current I is flowing, this is infinite, and we have to find the magnetic field here. So first of all, you'll have to just confirm one thing, that if we are finding the magnetic field of, suppose there is a wire, right? This is a wire, and we have to find the value of magnetic field on its own axis. So you should just say that the perpendicular distance of this particular point from this wire should be 0, because the perpendicular distance we are talking about, this is a wire and this is the point. There is no perpendicular distance. This is lying on its own axis. That means here, because of this wire, the magnetic field is 0. So just cut it. Here, because of this, magnetic field is 0. This is just a half ring. So B is equals to mu naught I. Suppose the radius is R. So mu naught I by 4R, because it is semicircular ring. Okay, great. Okay, next. Suppose you have a system like this. You have a system, something like this. This is a system. And we have to find the magnetic field here. Right? So this is a quarter. Now you will have to do it by yourself. This is a quarter ring. This is a semi-infinite wire. This is a semi-infinite wire, and this is a quarter ring. So if the radius is R and the current I is flowing, then you can easily find the value of magnetic field on this particular point. Very good. Okay. Next point. Or there are a lot of things also we can consider in this Biot-Savart law. We are not going to derive any expression, but we are going to see all the expression which are required for the JEE Main syllabus. Okay, next thing is, we have just solved the examples. Next thing is Ampere's circuital law. Okay, what is Ampere's circuital law? Ampere's circuital law is a bhai of that particular Gauss law. Gauss law is a brother of Ampere's circuital law, and Ampere's circuital law is a brother of Gauss law. So what it says, that we have suppose we have a lot of wires, lot of systems in which the current I flowing. Suppose this is a wire in which the current I is flowing in the forward direction or upward direction. Here the current I2 is flowing in the upward direction. Here current I3 is going in the downward direction. So cross is showing inside, dot is showing outside the plane. So here what Ampere's circuital law says, that if we have a system in which a lot of wires are there, then we have to find the value of magnetic field here. Suppose that on this particular point we have to find the value of magnetic field, right? So what we have to do, we just have to draw a circular loop or any kind of loop. This loop is called Amperian loop, right? Amperian loop. And because of this Amperian loop, or we can say the magnetic field, we just have to find the magnetic field here, right? So the value of magnetic field dot product with the length element, and you just have to do all these things on this loop, and the product of all these things means the closed integration of B dot dl. These are the vector quantities, dot product of the B dot dl, that is equals to mu naught times I in closed. Got it? Done. Next, so now there are a lot of applications of the Ampere's circuital law. If I say that can we find the magnetic field because of finite wire with the help of Ampere's circuital law? No, we cannot find. Is the Ampere's circuital law valid in the case of finite wire? Yes, it is valid, but we cannot do the calculations with the help of Ampere's circuital law. It is basically, we can say, Ampere's circuital law is valid everywhere, but we can do the calculation with the help of Ampere's circuit law only in the symmetric systems like infinite wire. So if we have infinite wire or like this, suppose that this is the infinite wire application. There are a lot of applications of the Watt-Savitt law. So if we have a wire, infinite wire, and the current I is flowing, and we have a distance r. Now we have to find the value of magnetic field here. So what you have to do, if you have any kind of system, if I say you have any kind of system, suppose that this is the wire and the current I is flowing, now you have to find the value of magnetic field here at a distance of r. Now you just have to do what you have to do, you just have to make an Amperian loop, right? Okay, now you have to make an Amperian loop. Here it is circle in this particular case. Now you have to find the value of magnetic field here. So what is the value of magnetic field? We just have to write the Ampere's circuit law. What is Ampere's circuit law? Close integration of B dot dl, that is equals to mu naught times I in. Mu naught times I in means B dot dl. dl is what? The length element. So B dl means the close integration of dl, that is equals to mu naught times what is the total value of current? It is I. So B into 2 pi r, that is equals to mu naught times I. So B is equals to what? Mu naught times I divided by 2 pi r. This is the value of magnetic field on this particular point. So if you have a hollow wire, if you have a solid wire, any kind of wire you have, you can find the value of you can calculate the value of magnetic field in any system, right? So if you have, I'm just going to show you the expression. If you have a hollow infinite wire, then it is like the solid conducting wire, or you should say hollow non-conducting wire. You can say this kind of system is like that. Okay, so here this is a hollow infinite wire, and you have to find the value of magnetic field inside as well as outside. So inside, the value of magnetic field is 0 because the total enclosed current inside the sphere or inside the cylinder, that is 0. Similarly, outside we have to find the system. So here we have to do the we have done the calculation. The calculation is same here, and we have found the value of magnetic field, that is equals to B is equals to mu naught I by 2 pi r. If we have to plot the graph of this particular thing, we can say that B is on the y-axis, R is on the x-axis. If this is the radius, then we can say here it is 0 0 0 0 0. Now it is decreasing with r. So something like this. This is the magnetic field. PYQ series of J means Nandini, it is also in the English, right, on the J infinity, right? So here we are just covering it in English, right? So if we have a solid wire, suppose that if we have a solid wire, okay, if we have a solid wire, then it is like, suppose we have this solid wire and we have to find the value of magnetic field. So inside the wire, the formula is mu naught I, mu naught J. J is the current density. J is current density here. So J is equals to I by A here. So you just have to substitute the value of J, and you can write the value. These are the formulas. This is the B inside, this is the B outside. But suppose that, let me take one example. Okay. Let me take one example. Suppose that this is the wire, which is a solid wire, right? This is a solid wire, and inside the wire, we can say the current density J is equals to K by R. J is equals to K by R, something like this. It can be a function of R. I should write the function of R, just a function of R. If it is a function of R, then you have to find the value of current. First of all, I is equals to integration J dA. Now you have to put the value of J here. It can be a function of R, and what is the area element? Area element is 2 pi R into dr. Now you just have to integrate the value of I. Then you will have to substitute I in this expression, B dot dl, that is equals to mu naught times I enclosed. First of all, you'll have to integrate, then you'll have to substitute the value of I. If it is asking inside, then it is like from 0 to small r, and if it is asking outside, then 0 to capital R. Done? Next thing. What is the graph of it? We can simply say that B is equals to mu naught JR by 2. It is inside, and B is equals to mu naught I by 2 pi r. It is outside. So inside it is proportional to R, something like this. Outside it is inversely proportional to R, something like this. So this is the graph of B versus R. Thank you so much. Okay. Next thing. If we have a solenoid. If we have you have to remember the formula of solenoid and the toroid. We can derive also, but we are not going to derive this particular expression. So B is equals to mu naught I that is the magnetic field because of this solenoid, inside which solenoid we should say. And if there is a toroid also, because toroid is not asked in the JMIN examination, it's asked in the board. So we just write the expression B is equals to mu naught Ni. This is also the expression used in the toroid. So this is in the solenoid as well as toroid. Thank you so much, Nandini. Thank you so much. Okay, next thing. This was, first of all, let me tell you one thing. I have told you in the starting of the session that there are two aspects. First is that how we can find the value of magnetic field. Secondly, how we can calculate the value of force. So first aspect was just to find the value of magnetic field that we have seen in a lot of systems. Okay. Next is how we can calculate the value of force. Why force? Suppose we have a current carrying conductor and we have a charge. Now, if we just give a velocity, some velocity v to this particular charge, this charge deviates. Okay, where suppose this is the magnetic field, so this is the wire, so magnetic field should be inside on this particular point. Okay, now what happens is, if we have given a velocity to this particular charge, this charge deviates something like this. Why it is deviating? Because magnetic field applies a magnetic force on a moving charge. So that particular force is given by F, that is equals to Q V cross B. This is the force which acts on a moving charge in a magnetic field. Now, since there is a magnetic field because of this wire and this charge is moving in the magnetic field, so we can say that force is equals to Q V cross B. Next, now let me tell you one thing. This is the force. This is the force. So if F is equals to Q V cross B, now there are a lot of options. Suppose charge of the velocity of charge is parallel to magnetic field. If V is parallel to B, so suppose this is B, and the charge is also parallel. Velocity of charge is also parallel. This is V, this is Q. Done. Okay. So look at me. If this is V and this is also B, what was the force expression? F is equals to Q V cross B. Q V cross B, right? Now listen to me. This is V and this is B. It means the cross product of V and B, that will be 0, because all those quantities V and B are in the same direction. So cross product will be 0 because you cannot curl your fingers now. So that's why this goes in the same direction which we have thrown. So the path of this particular particle is straight line. Got it? Next, if we have just thrown this particular, let me go to the next page. If we have thrown this particular particle of V, or we can say the velocity is perpendicular to B. If velocity is perpendicular to B, suppose the magnetic field is inside. This is the magnetic field. And we have thrown the charge particle perpendicular. To the magnetic field. Now, what happens is there is a force which is acting on this particular particle. F is equals to Q V cross B. Right? Now, since velocity is upward, look at me, velocity is upward and magnetic field is inside. That means F V cross B, F is equals to Q V cross B, means force is in this direction. It means particle will go in this particular direction. Right? Now, since the particle is going in this particular direction, now the magnetic field is inside. V there, B inside, V cross B, force downwards. It means it just comes like this. Now, velocity is downwards. So if velocity is downward and magnetic field is inside, V cross B means force is in this direction. Look at me, force is in this direction. So this is the force. Now, V there, B inside, V cross B means force is upwards. So it just goes like this. So this is a path of a particle which is moving perpendicular to the magnetic field. The path of the particle is circle. So what is the path? First of all, path of the particle is circle. And believe me, there are multiple problems on this particular concept. I should say every year from the magnetism, the problem is being asked from this particular topic. So now the question arises that if it is moving in a circle, there should be some radius. So the radius is R. What is the formula for the radius? If we should say the force is QVB and centrifugal force because it is moving in a circle. So that's why there will be a centrifugal force which is qv cross b, sorry, mv square by r, mv square by r. V got cancelled, this capital R, suppose that because that is capital R is equals to mv by qb, mv by qb. This is the formula of radius. This is the formula of radius of the particle which is moving in the magnetic field perpendicular to the direction of magnetic field. Great, great. So now next thing, if we have got the radius r is equals to mv by qb, mv by qb, now there are a lot of things also being asked in this particular section, that what is the time period. So time period t is equals to what, 2 pi r by v, 2 pi r by v. What is the value of r? Just substitute this. 2 pi r is mv by qb, mv by qb, or this is v got cancelled. Time period is what? 2 pi m by qb. This is time period. This is time period. If we talk about the angular velocity or angular speed, omega, that is equals to 2 pi by t. 2 pi by t, just substitute the values. So 2 pi by t is what? 2 pi m by qb, by qb. So by qb got upside, 2 pi got cancelled, omega is equals to qb by m. qb by m. This is the value of omega. Done. Next thing, just look at this. This was the figure. This was the figure. Now just imagine one thing, that this is going in a circle, and first of all, if you talk about the direction of force and direction of velocity, since velocity is in direction, now at this particular instant when the velocity is upwards, what is the direction of force? Since v is this and b is inside, so direction of force is this, right? Means v and b are perpendicular. V and b are perpendicular on this particular point. V is this, v cross b, force is downwards. So v is this and force is this. So force and velocity are always perpendicular in this particular case. Done. So if f and v are perpendicular, it means we can say that the displacement is also perpendicular to the force. Okay. So if the displacement is also perpendicular, if displacement is also perpendicular, displacement or velocity is perpendicular to force, it means that the work done, because what is work done? W is equals to F dot S, and there it comes as Fs cos theta. So if the angle between S and F is 90 degree, cos theta becomes 0, means work done is 0. So work done is 0. Now on this particular concept, there are a lot of problems which are being asked. So if work done is 0, it means we can say that the particle is moving, suppose there is velocity v, it will not change its velocity, means the velocity, or we should say the energy of the particle, is conserved. So this is a very important concept. If a particle is moving in a magnetic field perpendicular to the magnetic field, then the work done, or we should say that the force on the particle is always perpendicular to the displacement. That's why the kinetic energy is always conserved. Kinetic energy is conserved. Kinetic energy is conserved. Got it? Next thing. If we have the particle which is like, suppose this was the magnetic field. This was the magnetic field, and the particle started moving at an angle theta. This is velocity and this is theta. So if we have given a velocity perpendicular, sorry, v at an angle of theta, v at an angle theta, with b. If v and b are at an angle theta, then we just do the components of velocity. One component is the direction v cos theta, and this component is v sin theta. So now if we say the velocity which is parallel, like this, v cos theta is parallel to the magnetic field, that means this velocity, if it is parallel to the magnetic field, then we should say that there is no force on this particular component. It means it will ready to go, or it will just go in the same direction as the magnetic field. Next, if we talk about the v sin theta, it is perpendicular to the magnetic field. It means we can say if the velocity is perpendicular to the magnetic field, the path is a circle. So the particle is doing circle as well as straight line motion, means the particle is going like in this particular path. So this is called the helical path. This is called the helical path, something like this. So this is the path of this particular particle, and this is called the pitch. The distance between two chakras is called pitch. This is called pitch. Okay, and we should say that the radius in this particular case r is equals to mv by qb, and what is the velocity which is responsible for the circular motion? That is v sine theta, right? So mv sine theta, or we should say v perpendicular, because there he could say that this is theta, so we should write v perpendicular, mv perpendicular by qb. But in this particular case, v perpendicular is v sine theta, so mv sine theta divided by qb, divided by qb. This is the radius, right? Now, clear, done, very good. So first of all, let me tell you one thing more, that if we are talking about the pitch, what is the value of pitch? What is the value of pitch? Pitch is equals to the velocity in this particular direction and multiplied with the time period. So v parallel into t. What is t? What is the time period? Time period is basically t is equals to 2 pi m by qb. It doesn't depend on the velocity. It does not depend on the velocity. It means we just have to substitute the values here. It means 2 pi m into what is the velocity in this particular direction? V cos theta. 2 pi m into v cos theta divided by qb. So this is the pitch. So anything can be asked in this particular question, that what is the pitch, what is the time period, what is the radius of the particle. So that's all the things. Okay, next thing. Next, if we have a particle which was moving in the magnetic field, but now we have introduced an electric field as well. Now we have introduced an electric field. Okay, thank you so much. So now we are talking about the magnetic field plus electric field, right? So suppose that first of all, let me talk about the force which is being going to act on the particle which is moving in the magnetic field as well as the electric field. So both fields are there. It means both forces will work. So first of all, what was the electric force? That was the F is equals to Q into E, right? And what is the magnetic field? F is equals to QV cross B. And if we just combine these particular forces, then the force becomes the Lorentz force. That particular force is called Lorentz force, and that is equals to QE, which is the electric force, plus QV cross B. Got it? Got it? Okay. So, what is that Lorentz force? Lorentz force. What is Lorentz force? Lorentz force is F is equals to QE plus QV cross B. QV plus QV cross B. Now, if we talk about the path and how particle going to be react in the particular electric field plus magnetic field. So first of all, let me tell you one thing, that if the particle is moving, and first of all, V is parallel to E as well as B. Okay, all the V, B, E, all the parallel, right? So A is also in this direction, B is also in this direction, velocity is also in this direction. So this is the direction of E and B, and velocity is also in this direction. Velocity is also in this direction. So this is V, this is V. So if we talk about the magnetic force, like if the particle was in, suppose that we should say in the electric field. If the particle was in electric field and it is going in the direction of electric field, then we should say that there is a force QE which is acting on the particle, right? It means the particle will accelerate because of that particular QE, right? But if the particle is moving in the direction of magnetic field, then there is no force which is going to be act on the particular particle. That means there is no acceleration because of that particular magnetic field. So when the particle was alone moving in the magnetic field, then it was not accelerating, it was moving with a constant velocity. But if it is moving in combined electromagnetic field, then it will accelerate. It will not change its path as well, but it will accelerate. It will continue to go in the particular direction, means path is equals to, what is the path? Path is simple straight line. Path is straight line. But remember this particular thing, that particle is accelerating, it is not moving with the constant velocity. Okay. Oh, thank you so much. Okay, next thing. Yeah. Now, if the velocity and the electric field and magnetic field are in the same direction, but velocity is perpendicular. Okay. So V is perpendicular to E, which is parallel to B. Okay, so now if we talk about the electric field and magnetic field, these are in this direction. This is E and B. Next, Now we have given the velocity perpendicular to it. This is v, which is perpendicular to E and B. Okay. Now just remember one thing, that if this is velocity, it means there is no force in this direction because of the magnetic field, right? So magnetic field is trying to move the particle in the circle, right? Now, what electric field does? Electric field just applies a force on this particular charge q in the direction of electric field. It means the particle will go in this direction because of electric field, and it will just continue in the circle because of the magnetic field. It means it is going in the helical path in this particular case as well. So we can say this is going in the helical path with the increasing pitch because a force is there. Why I'm saying increasing pitch? Because there is a force in the direction. It means the velocity will continuously increasing. That means the pitch will also increase. It means this is pitch and it is increasing. This is increasing. This is increasing. Path is helical. Path is helical. But initial velocity in this direction is 0. So this should be also there. Initial velocity in parallel direction in x direction. In x direction is 0, but if we talk about the if v is at an angle, if v is at theta with E and B, so if this is E and B, if this is E and B, and the particle is at an angle theta, so this is theta, sorry, this is magnetic field, velocity, and this is angle theta. So this is v perpendicular, this is v perpendicular or v sine theta. This is v cos theta. It means here the initial velocity is also in this direction. So here the initial velocity is in x direction is not 0, but the path will again be the helical with increasing pitch. So path is also same, but the difference is in this particular case is initial velocity is not 0. Very good, very good. Next thing. Now there are a lot of questions which are being asked on this particular thing, that if we are throwing a particle in the magnetic field, then what will be the path? A lot of things. So what kind of questions are being asked in the JEE Main examination? Just understand the question pattern, that suppose we have a magnetic field, and in the magnetic field we just have entered two particular particles. Two particles are entering. Two particles are entering. One is alpha particle, one, and the second, or we should say one is proton, one is electron, and it can also say three particles. So we can just say alpha particle, neutron, a lot of things are there, and it will say a lot of things. That first of all, it will say that particles are entering with same kinetic energy. These are the cases which are being given in the question. So same kinetic energy, or it should say same potential difference, or it can say same kinetic energy, same potential, same momentum. It can also say same momentum. So if the two particles or three particles or more than three particles are entering in the magnetic field with this particular thing, like same kinetic energy, same potential, same different momentum, then it asks that what is the ratio of radius. So what was the formula of radius? There is simply magnetic field and particle is entering perpendicular. So R is equals to what? mv by qb. R is equals to what? mv by qb. Now you just have to reform this particular formula in the terms of kinetic energy or potential difference or the momentum. So we can write half mv square, that is equals to kinetic energy. It means we can write v is equals to under root 2 kinetic energy by m. So if we just substitute this relation here, we got R is equals to under root 2 km divided by qb. So this is the value of radius. Now if it is saying that the particles are electron and proton, so kinetic energy is same, but you know the difference between the masses. You know what is the mass of electron, you know what is the mass of proton, you know the charges. If it is saying the same magnetic field, then BB will get cancelled. He is saying that what is the ratio of radius, right? Okay, so this is how we can find the value of ratio of radius. And if it is saying about the same potential difference, we can write, we have this formula, R is equals to root 2 m kinetic energy divided by qb. So we can also convert it. So R is equals to what? Root 2m kinetic energy is what? Q into V divided by QB. So if it is talking about the same potential difference, you will just apply this particular formula. Right? If it is saying same momentum, so R is equals to what? Mv by Qb. Mv is what? Momentum. So P by Qb. So this is the formula in terms of momentum. So whatever it is saying, we just have to substitute the values of Q and V. Momentum got cancelled. We just can simply find the value of ratio of the radius. Done? Okay. Next thing is a force. I should say force on a current carrying conductor. 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 So if it is a current carrying conductor and it is placed in a magnetic field B, here it is a magnetic field B, then we can write the expression of force on this particular wire F, that is equals to I L cross B. This is the value of force on this particular wire. Right? How we are going to find the direction of magnetic, how we are going to find the I should say the direction of magnetic, direction of force. Direction of force. So how we can find the direction of force? L, which is the direction of current as well. So just place your fingers in the direction of current, means these are the direction of L. Now you have to curl your fingers in the direction of magnetic field. It means L cross B, means thumb is in this direction, means the force on this particular wire is in this direction. So this is how we can find the value of force. Okay, now suppose we have a system like this. We have a system like this, and we have the wire something like this. This is a wire. This is point A, this is point B, this length is L, this distance is D. So if we are going to talk about the force on this particular wire, then what should we write in this particular expression? L or D, means the distance or the displacement between the initial and final points, or the total length of the wire. So in this particular expression, we are using this, the displacement, or we should say that the displacement between A and B. So we should write in this particular case F is equals to Q D cross B, not L cross B. Q D cross B. It can happen in some cases like this. If we have wire like this, it is in the magnetic field and current I is flowing, then we should take the diameter. So 2R is the distance we should substitute here in the case of D. Done till here? Okay. Next thing is if we have the suppose two infinite wires, something like this. This is one wire I1, and these are two second wire I2, the distance is D, and we have to find the force between these two wires. So if we write the magnetic field because of this first wire B1, that is equals to mu naught I1 divided by 2 pi D. So magnetic field is magnetic field is B1 here. Now we can write the force F2, that is equals to IL cross B, right? So I2, L is what? L is D, and what is B? B1. IL cross B means D is what? L is the length, I is the length of wire, IL cross B. So what is the length? Length is infinite. So in this particular case, we don't find the exact value of force on the entire wire. Rather than this, we just find the value of force per unit length in this particular cases. So force per unit length, that is equals to what? I2 into B1. B1 is what? Mu naught I1. This I2 divided by 2 pi D. This is the force per unit length between two infinite wires. Great. Should we move on to the next thing? Definitely we should move on to the next thing. Okay. Next. There are a lot of problems like this. Suppose there is a system like this. This is a wire in which current I is flowing, and at a distance A there is a square of side A. And we have to find the value of force on this particular square, right? How we can find the value of force? So we just have to think individually, like about this particular side. If we talk about this side, the length of the side is A, so we can write F on this particular wire. So first of all, what is the direction of force? So if we say the direction, so this is L and B is inside. Force is in this direction. So if it is F1, so F1, that is equals to QV cross, IL cross B, right? So I is what? Current I is flowing here also. So L is what? A. So IL cross B. B is in B on this point. So because of this particular wire, B will be equal to mu naught I by 2 pi A. 2 pi a. So what is mu naught a got cancelled, mu naught I square by 2 pi. This is the force on this particular wire. Now if we talk about this wire, so F is equals to I L cross B. So L is in this direction, B is inside, so force is in this direction. So this is F2. F2 is equals to mu naught I by IL cross B, right? So IL is what? A, B is what? B is in this direction or on the distance 2a. So mu naught I divided by 2 pi a. A is what? 2a. A is what? 2a. A got cancelled, mu naught I square divided by 4a. This is the force on this particular segment, right? Okay. Got it. So just listen to me very carefully, that if we are talking about this particular system, in this particular system there are 4 wires, right? 1, 2, 3, 4. First of all, we are writing the forces on this and this segment. So if we talk about F1, F1 is what? ILB. So IL is the length of the wire and this is B. So if we talk about the force F1, this we have got this. Now if we talk about the F2, F2 is at a distance 2a. So first of all, ILB is at distance 2a from this infinite wire. So this is 2a, just substitute the value of this and we have got force is in this direction. Now if we talk about the forces on this, suppose this is F3, how we are writing the direction? First of all, let me clear you that this is the L and this is the B. So force is upwards. So this is F3. Similarly, this is the L and this is the B. So force is this, means this is F4. Now, what are the values of F3 and F4? I'll just tell you one thing, that just imagine this, that we have this wire and this segment A. This is distance A and this is the current I. So if we talk about a little segment, if we talk about the little segment of, we can say X dx, if this is a little element, on this particular element the force is in this direction, upwards, right? Similarly, if there is segment here and on this segment dx is equals to dx, the force is in this direction. So this force and this force got cancelled. So that's why this element got cancelled, this element got cancelled. So it means on the upper and the lower wire, all the forces are just cancelled, right? Very good. Now if we talk, now since F3 and F4 are cancelling each other, F3 is equals to F4. F3 is equals to F4. It means the total force in this vertical direction is 0. So net force is what? F net. If we talk about the F net, that is equals to what? F1 minus F2. F1 minus F2. What is F1? What is F1? F1 is this, mu naught I square by 2 pi minus what is F2? Mu naught I square divided by 4 pi. So it will be simply mu naught I square by 4 pi. This is the value of F net. This is the value of F net. That's it for this particular question. Done. Next. This we have talked about. Next we have to talk about the magnetic moment, right? Next we have to talk about the magnetic moment. So magnetic moment. So what is the magnetic moment? It is just the property, we should say, that if we have a loop, in this particular loop a current I is flowing, the area of the loop is A. Suppose that this is a loop, current I is flowing, area is A, and suppose the number of turns in the loop is N. So I should say that the magnetic moment is showing the we should say that the strength of this particular loop, or we should say the magnetic field strength of this particular loop. So the magnetic moment M, that is equals to NIA. This is the direction, sorry, this is the value of magnetic moment. Just a second. This is the value of magnetic moment. And if we talk about one more thing here, that what is the direction of magnetic field? If we talk about the direction, so direction is in the area vector direction. So if this is loop, the current I is flowing in this direction. So what is the area vector? Area vector, I should say, in the open systems, this is the open system, right? So in the open systems, the area vector is always perpendicular to the surface. If we talk about this thing, so let me elaborate this. This is the open system, right? This is a loop or we should say this is a surface. So because of this surface, area can be in two directions. One is this direction, right? And second is this direction. So there are two directions of the magnetic field, sorry, area vector. So, but what direction we have to choose? This depends on the current, right? So if the current is flowing in this direction, it means we can say the area vector is inside. So area vector is inside. Area vector is inside. If the area vector is inside, it means the magnetic moment is also inside. So we'll have to take the area vector according to the value of current or according to the direction of current, and then we'll have to choose the direction of magnetic moment accordingly. Done? Any doubt? So this is the magnetic moment. And next thing we have to remember in our mind that if we talk about a particular quantity, there is a fixed quantity which is called the ratio of magnetic moment and angular momentum. Just listen to me very carefully. Ratio of magnetic moment and angular momentum. So magnetic moment is simply m and angular momentum is L. This ratio is always q by 2m for a system. This particular expression is also used to calculate the value of magnetic moment for a particular system. Suppose that we have a particular solid wire. So yeah, solid sphere. This is a solid sphere. So I should make the solid sphere properly. Suppose this is a solid sphere. Okay, and let me make it solid as well. So this is a solid sphere, and it has some charge q. It has some charge q over it. So if it has some charge q over it, this is a solid sphere. This is a solid sphere, and it has charge q over it, and it is rotating with angular velocity omega. Now, if the question is something like this, that we have to find the value of magnetic moment of this particular wire. So this is a very tough process, that we have to take the elements, we have to make the rings, or a lot of things we can make the, so a lot of things can happen here. But if we just apply this particular formula, then this process can be very simple. That how we can calculate the value of magnetic moment from this particular formula, m is equals to q by 2m into L. So just remember this formula so that we can calculate the value of, so I'm just going to calculate also. So if we talk about the angular momentum, L is equals to what? I into omega. What is I of this solid sphere? This is simply 2 by 5, mass is m and radius is r. So m 2 by 5 mr square, right, into omega. This is the value of L. Just substitute the value of L here. We will get m is equal, this is magnetic moment, right? So I have to write mm because there is one m also here. So to q by 2m, q is capital Q here, q by 2m into 2 by 5 m r square omega. 2 got cancelled, got cancelled, q r square omega divided by 5. This is the value of magnetic moment in this particular case. Done till here? Any confusion, any doubt? Should we move on to the next thing? Definitely we should move on to the next thing. Magnetic moment we have done. Now just one, two more things in the theory section. That if we talk about the torque, that tau is equals to what? Tau, suppose we have a loop here, and this is the loop, and it is kept in a magnetic field. And a current I is flowing. So torque, the formula of torque is m cross b. I'm not going to derive this particular expression. I'm just going to tell you that what is the meaning of this particular expression. M is, as I have already told, that m is the magnetic moment. A magnetic moment has its own direction in the area vector. So if the current is in direction, it means the magnetic moment is inside, and b is also inside. So in this particular case, torque is 0. So as we have said that this is the torque. Now let me give you some PYQs as well. This was about suppose this is the example of, this is a question of JEE Main 2024. What the question is saying: to insulated circular loop A and B of radius A carrying a current I in the anti-clockwise direction as shown in the figure, the magnitude of the magnetic induction at the center will be. So we have to find the value of magnetic induction or magnetic field. So just look at the systems. Just look at the system. This is a magnetic field. Sorry, this is a wire in which current, suppose that I is flowing. So what is the direction of magnetic field? So just curl your fingers in the direction of current. So this is the direction of current. It means magnetic field is in this direction. This is magnetic field, and B is equals to what? At the center, mu naught I by 2R. Now this is the, like this, in this plane. It is in this plane. It means if we curl the fingers like this, then the magnetic field is in this direction. So B2 is in this direction. It is as well mu naught I, because same system. So 2R. Now to same magnetic field perpendicular, it means net will be in this direction. B is equals to what? B root 2. B net is equals to B root 2, because perpendicular, right? So mu naught I root 2 divided by 2R. So this is the answer for this particular question. Or I should write this root 2 got cancelled. Here root 2 is remaining. So mu naught by I by root 2A, because A is the radius in this particular case. Got it? Any confusion? Any doubt? No? Let's move on to the next question. As I have told you that these kind of questions are being asked on the regular basis, I have told you that how to solve this particular question. Because of this, magnetic field is 0 at this particular point. Now there is just a semicircular ring. And you can find the center, the magnetic field at the center of the semicircular ring. Formula is what? B is equals to mu naught I divided by 4R. Mu naught I by 4R. Similarly, I have also shown you that this kind of question, there are three systems: 1, 2, 3. So first is semi-infinite wire. Second, because of this, since this point is lying at the axis of the wire, so this is cancelled. This is the semicircular ring. So mu naught I by 2R, sorry 4R, semicircular, right? 4R plus this is semi-infinite, means mu naught I by 4 pi R. So just this is the answer. This is the answer. Done. Next thing. These kind of questions are being asked on the regular basis, that how we can, this can give a rectangle, this can give a triangle, this can give a hexagon. So just keep this thing in mind, that if we have a system like this, then what we have to do, just we have to calculate the angles first of all, that this is a side, right? So side is what? Side is 4 root 3 centimeter. If side is 4 root 3 centimeter, total side is 4 root 3 centimeter, it means this total angle, because total angle is 360. Now, I got one comment on the other channel that I, in this particular question, I've said that the total summation of the angles is 360, right? I have said, just look at this. I have said that the total summation of the angles is 360. Now one student is commenting that how you can write the summation of all the angles is 360. It should be 180. Now what I am saying and what he is listening, the difference is this, that I am saying that all the summation of this angle is 360. This is 360, right? He is saying that all the summation of these angles is 180. Just listen to the thing which I am saying. He is saying that this is the thing. And he is laughing at it, that I am saying that the sir is said that this is angle is 360. It should be 180. So just listen to the things which I'm saying. So if the total angle is 360, then this angle, this is 1/3 of this. So this is 120 and half of this is 60. This is 60 and total is 4 root 3, means half is 2 root 3. This half is 2 root 3. So if we talk about this triangle, this is 2 root 3, this is 60 degree. We can calculate this. So if it is x, so we can write tan 60. Tan 60 is equals to 2 root 3 divided by x. Tan 60 is what? Root 3. So root 3 got cancelled. X is equals to 2 centimeter. So if we have calculated x, we have calculated these angles. So B is what? B is equals to mu naught I by 4 pi R into sine theta 1 plus sine theta 2. Now what are the values of theta 1 and theta 2? Theta 1 and theta 2 are 60 degrees. Theta 1 and theta 2 are 60 degrees. That's it. Okay, so just substitute the values here. Now don't forget to multiply with the 3. 1, 2, 3. There are 3 sides. I is 2 ampere, theta 1, theta 2, 60 degree. Distance is 2 centimeter. Convert it into the meter. Then you can find the answer. I'm not going to calculate. I'm just going to say that just solve these problems. Right? Next thing. I'm not going to take all the problem. This is a problem from JEE Main 2023. You can see the systems, lot of systems here. The combination is also here. I'm not going to solve. There are a lot of combinations, right? So these types of problems are being asked on the regular basis. Okay. One more thing that I should show you. that what kind of questions are being asked. Some not that much complicated problems are these are. This is a good problem. This is a good problem from AIEEE 2010. What the problem is saying, that two long parallel wires are at a distance 2D apart. They carry steady currents, equal currents flowing out of the plane. Okay, these are the wires, right? These are the wires. These are the wires. Okay. Out of the plane, the variation of magnetic field along the x dash axis, x axis is this. This is the x dash axis. So the variation of magnetic field is given by, what is the variation of magnetic field? So I should say that just draw these lines so you can calculate very easily, right? Suppose there is no wire here, okay, and one thing you should remember, that because of this wire, because the current is outside now, so magnetic field is upside. At this particular point, magnetic field is upside, right? And because of this, magnetic field is down. It means here the magnetic field is 0. So in between the wires, the magnetic field should be 0. It means you can first of all neglect the options. So what is 0? 0, 0, 0, 0, 0. This is not 0. This is not touching 0. This is also not touching 0. And these options are neglected. Now we just have to compare these options. Just compare these options. Now if we go towards this, it means the magnetic field is upward is more and downward is less. So magnetic field is in upward direction, and here the magnetic field is in the downward direction more and upward is less. It means here the total is downwards. It means we can say the graph should be like this. But here in bit, because the 2D and the equal currents, it means the equilibrium point, I should say, that where the magnetic field is 0, that means this is in the middle. So here in this option, it is not showing in middle, but also you should consider one more thing, that if you come here, like near the wire, if I talk about this wire and if I talk about the axis, just look at this, okay. So if at this particular point the magnetic field is in this direction, downwards, but if we talk about this direction, so magnetic field is in upward direction, means magnetic field is changing the direction. So here the magnetic field is in the same direction, but here the magnetic field is in the different direction. It means option A will be correct, because magnetic field should change its direction. Very good, very good, very good. Okay, done. So this session was all about that, how we are going to solve the what are all the concepts. I just scheduled this class because I wanted to show all the concepts, all the variation of problems. I'm not going to solve all the PIQs, that is a different session. So that's it about this session, because in this session we were planning that I should revise all the theory in a very short duration. So in 1 hour we have revised all the theory, some PYQs as well, some examples as well, and I've told you that what kind of problems are being asked. So this can be the most effective session for you if you are preparing for the JEE Mains second attempt. So that is it for this session. If you have any doubt, any confusion, then you can write in the comment section. A comment section is only for you. So see you in the next section. Okay, bye bye. Any doubt? I'm going to end the stream. Okay, thank you everyone for joining the session. Okay, bye bye.